This unit covers networks forensics, and within it we'll try and understand some of the methodologies that we use to analyze network traces. We'll try and develop an in-depth understanding of some of the key network protocols, including IP, TCP, Arp, Icmp, DNS, and some application layer protocols, and then also define a range of audit sources that we can analyze to see network activity. The core of most network traffic, especially traffic that goes to and from a host, is based around Ethernet, IP, and TCP. And normally when we abstract the way that data is sent, we look at it in a layered model. This makes it easier to analyze, simpler to abstract at different levels, and also makes the interconnection of protocols and equipment easier. So we normally start with the original data, then we add some application layer protocol onto it. So this can include HTTP, FTP, Telnet, SNMTP, and so on. And it's this type of information that tends to be used to be able to interpret the data in the correct way. Then below that we have the transport layer, and the main objective of the transport layer is to segment the data and to rebuild it back up into the original data source. At this level we get a connection between two entities. Then below that we have the network layer, and the network layer is there to ensure that we can get delivery of data packets as they leave one host and arrive at the other. Then we need to encapsulate this network layer or data packet in some format. So we typically add a header and a trailer onto it and wrap it within inside a data frame. So the most popular data frame is an Ethernet data frame, and this represents the data link layer. Then we transmit it using layer 1. Often when we view the traffic on a network, we view in different levels of abstraction. So we could look at the local network traffic within inside the Ethernet layer, the data as it's transmitted across the internet within the IP layer, the data that's transmitted between two application programs in the TCP layer, and so on. The core of most communications on the internet is built around the client-server three-way handshake. With this, initially a host connects to a server. The first TCP segment which is sent has a SYN flag set. Then the server, if it's willing to accept the connection, will send back a SYN acknowledge. If this is acceptable, the host will send back an acknowledge, and the connection is bound after this. The key parameters involved are the ports, the TCP ports on either end. A key element of the TCP protocol is that it's connection orientated and it is also reliable. And the reason that it is reliable is that it uses a series of sequence numbers and acknowledgements. So in this case we can see we have sequence number 1, sequence number 0 followed by sequence number 1, and so on. Over here we have sequence 1, sequence 0 followed by sequence 1. The acknowledgement is sent back from one machine to the other to say the next data segment that it expects to see. So in this case the server sends back to the client that it expects to see sequence number 1, and it is in this way that the server acknowledges that it's received the data to the client. So once we have the handshaking, then we can transmit data. So we can see in the example here, then when the data is transmitted, the server, the host in this case, acknowledges that it's received up to byte 27 and expects to see 28 as the next sequence. As we can see here, the next part of the sequence is 28. At the same time, the server acknowledges that it's received the previous data segment. So in this way, the client and the server can act in a reliable way. Another part of this negotiation is the window negotiation. With a window, we negotiate the number of data segments that are allowed to be transmitted before one side has to wait for an acknowledgement from the other. So in this case, the host says that it's willing to receive 8,192 data segments before it will wait for an acknowledgement. So let's have a look at the main elements of Ethernet, IP and TCP. So with TCP, we have what's called with Ethernet, we have what's called the preamble, and basically that's just a series of ones and zeros. So we have 8 bytes of this, followed by another byte which defines the start of the Ethernet frame. Next we have the source and destination physical addresses, and these are 6 bytes long. And the true strength of Ethernet is that it can carry many different types of layer 3 protocols. So if we have hexadecimal 800, which is 1000 and then 8 zeros, then it identifies that the next thing that's coming with inside the data is an IP data frame. If it's 806 hex, then it's ARP, and so on. So Ethernet can carry a number of layer 3 protocols within inside itself. Then at the end we have a checksum. For the IP header, we have the version number. So typically this will be version 4, which looks like this, or it might be version 6, which looks much different. Then we have a type of service, the identification, time to live, and the protocol field. And it's the protocol field which will define what layer 4 protocol is coming next. So if this is a 6, then it's TCP. If it's a 1, then it's Icmp. After this we have the two 32-bit source IP and destination addresses. The TCP field, the main two parts of it are the ports, the TCP source port and destination port, and we can also see the 32-bit sequence and acknowledgement numbers. With inside here we see the flags such as SYN, ACK, FIN, push, reset, and so on. This contains the window here. So let's look at an amazing little protocol called Arp, and it's Arp that possibly makes the internet so dynamic in that we can actually connect a computer to the internet and it can be discovered by all of the other hosts on the internet. And it's Arp that does the resolution of the last part of the network connection and often shows traces of initial connections to a network. So what does Arp really do? Well, it would be extremely difficult for us to be able to find out what the actual physical address of a remote computer actually was, because to be able to communicate with another computer, we need both its logical address, such as its IP address, and also its physical address. So if we wanted to communicate with a computer on another network, then it would be almost impossible to find out what its MAC address actually was. So what we do is that we use its logical address to be able to get the data packet transmitted across the internet, and then the last part of the connection, and also the first part, we use the Arp protocol to be able to discover what the MAC address actually is of the destination. So in this way, a host here can find out the gateway and communicate with it, and then routers in between can then route the data packet based on its logical address until it gets to the last part of the connection, and then it is up to Arp to be able to resolve this last part and to be able to produce the final delivery of the data. So in this case, we have a node here at 75.1, and it wants to communicate with something out with the network. So the first thing it must do, if it's just connected to a network, is that it must discover the MAC address of the gateway port, in this case the gateway port of the router. This is at 75.132. So if it hasn't discovered the MAC address of the default gateway, it sends out an Arp request broadcast to the whole of the local network, and this is bounded by a router. So routers do not send the Arp broadcast over to other ports. All the computers listen, and if they hear their IP address, so in this case the gateway will, then the gateway port sends back a directed reply back to the host. If we use a switch, then no other computers on the network actually hear the reply. If you use a hub, then all the other nodes will hear it. So then the node adds this to its Arp cache, so it doesn't have to rebroadcast it for a certain amount of time. When it has this, it can then communicate with the default gateway port MAC address and with the IP address of the destination. So then we go through the whole of the internet, changing the MAC addresses of the local router ports until we get to the last router. The last router then will do a broadcast for the destination IP address, and then it should be able to resolve the MAC address and deliver the actual data. So let's see this, how it occurs. So in this case we see the Arp being broadcast to the network. So in this case we can see the source is the local MAC address of the computer, and we use the broadcast address, which is all ones, and this is the broadcast here. Then the Arp reply comes back such as this, and we can see now there is no broadcast. It comes from this MAC address here and is sent directly to this MAC address here. The first part of a MAC address typically identifies the manufacturer, so in this case it's a VMware adapter, and we can see here that the reply says this is my address and this is what my MAC address actually is. Okay, so that's an Arp reply. So we're going to have a look at this. So we normally find that before some form of activity there is an Arp request to be able to resolve the addresses. So let's have a look at this in Wireshark. So here is our Arp request. So in this case we're requesting the target address. In this case we're asking for 75.2, and we'll tell us as we're at 132, and then here is the reply coming back again to actually define the MAC address. Another key element that we have inside our network traces is the trace of a SYN flag inside the TCP packet, and this often shows the start of client-server communications. So to recall again, what we basically have is that a client wants to connect to a server. The server waits on a certain port, TCP port. So the client sends a SYN on the port it wants to use to the server port. If the server accepts it, then it sends back a SYNAC to the client, and then the client sends back an ACK, and this is defined as the three-way handshake. So here is the trace. So you can see here that this is the source sending to the destination on TCP from its own local port, which in this case has been identified as 3655, which has been given a name there, and that gets connected to the FTP port with a SYN flag. So we see here that the sequence number is set. So the reply comes from 132 back to .1 and comes from the FTP port back to the 3655 port with a SYNAC, and in this way the server is saying that it now expects to see data segment 1 next. After this, we actually see data segment 1 coming from the client, and we see an ACK coming from the client to the server. So this shows the three-way handshake. So if we have a look at one of our traces, so this shows an example of SYN, SYNAC and ACK. So in this case we're connecting to the telnet port. So just have a look at that in Wireshark. So our connection happens telnet, we have SYN, SYNAC and ACK. So we can look at the detail of this. So here are our flags. Okay, so there's the SYN flag set. We then have a SYNAC, SYN and an ACK, and then we have an ACK. And these two addresses plus the two TCP ports should be unique across the whole of the internet at that given time. So now let's look at an example of an application protocol. And the one thing to remember about many of these application protocols is that they were developed at a time when we had a simple terminal which connected to a mainframe. So many of the commands were actually typed in manually and then a response came back. So application protocols such as FTP, HTTP have all grown up from this original teletype model. So we'll see a lot of commands that look as if they've been typed in. So with FTP we connect to port 21. So after we've connected, we can then use one of our commands. So the commands include ASCII, binary, buy, change directory, get, and so on. When we send these, we get a response, which is a numeric response that comes back. So codes that have that are between 100 and 199, our request action has been taken. 200 codes mean that the action has been successful, and so on. So examples are 200 means that the command is okay, 202 the command not implemented, and so on. User logged in is 230. A password required is one of the 200 codes. Entering passive mode is 227. So an example interchange. So once we connect, we'll see the 220 message coming back to say that it's now ready. So the first command that we can send is we define the user. So now we need well, it's actually a 300 code. 331 code defines that a password is required. Feed in the password, and if it's successful, then we get a 230 code, which is that the user is logged in. Syst will show what operating system we're using, so in this case it's Windows NT. PWT shows the present working directory, which is the top level in this case. And then many FTP systems use passive FTP. With passive FTP, we can actually see what the server IP address is, and as we'll see also which port it's going to open up for the communication. So port 21, the connection port, is only used for the commands and responses. When data is to be transmitted, in passive FTP, the server sets up a port to connect to, the client then connects into it. So the list is useful for getting a list of the folder. Change working directory allows us to change the current directory, and so on. We can set ASCII and binary here, and this is an example of us transferring a file to the FTP server. So we can see here we have our commands, and then we have our responses. With passive FTP, we obviously have our commands and responses in the same way, but if we need to make a listing or get data to be transferred, then we go into a passive FTP mode. So in this case, the string that comes back is important because it defines the IP address that we need to connect to, and also the port number. So in this case we have 4 and 23. So the calculation is made, such as this. So it's 4 times 256 plus 23 gives us port 1047. So then the client will make a connection on to that port with a SYN, SYNAC, and then an ACK, and the port's created here, and the data can be transferred, after which we get the normal FINAC at the end of it, and we should see a transfer complete. So let's have a look at an example of this, and we'll look at our FTP trace. Okay, so here is all our commands that we would normally have, and then we have our passive, and we can see here that a port has been opened up here. So we'll have a look at this within Wireshark. So here's the passive mode coming back. So it's 4 and 22. So we can see that in this case the port that's opened up is 1046. So that should be 4 times 256 plus 22. The port that our local machine is used is 3656, which differs from the the other TCP connection, which is 3655. So this shows an example of the data being transferred. So this is the connection being set up here, and the data is transmitted, and then we see the reply, the connection being closed here. Okay, so we can see other examples of the data being transmitted. A protocol that can be used to discover the host that connected to a network or the routes that the data takes is Icmp. With Icmp we have a fairly simple protocol which is carried inside an IP packet. So in this case what we have is that we have a request, an Icmp request type 8, which is an echo request, has a certain sequence number so that we can match up the reply when it comes back, and the data we typically see is EBC, D, and so on. So when a ping occurs, an Icmp 8 echo request goes out, and then we get a 0 echo reply, and again, as we said, the sequence number matches up that. If we can match up the sequence number and we measure the time it takes between sending and receiving, we can measure the latency between the two machines. Okay, so let's have a look at an example of some Icmp. This shows an example of a trace. So we can see here this is an example of the ping payloads. So we'll just have a look at this within Wireshark. Okay, so here we are, and we can see we're using Ethernet and IP. So we have a type 8, which is a ping request, and then the data itself is just the sequence that we identified earlier. This is the ABCD and so on. And then we have our reply. So in this case it's a 0, and we can identify the sequence number that's coming back again. See, the next one is a sequence 18, 19, and so on. So this allows the actual requester to match the replies as they come back. What we have here is hexadecimal representation of the ASCII characters. So 61 in hexadecimal is 01100001, which represents a lowercase a. Another protocol which shows normally the start of some form of trace of activity is DNS, which is used to map a domain name into an IP address. So the way that it works is that a local machine wants to access a destination, and all the machine actually knows is what its domain name is. So this domain name has very little relevance to the internet, and especially for the intermediate devices, so we must resolve this into a destination IP address. So it's DNS which is used to resolve this domain name into an IP address. So the way that it works is that we have the domain which is responsible for mapping the domain name into an address, and within inside this there is an A record defined for the domain name, which will resolve the IP address. We can also have a CNAM, and a CNAM defines the different aliases for the domain. So in this case, our host requests from a local DNS with a query as one of the flags of the DNS request. The opcode is 0. It asks for a recursive lookup, and recursive means that if the local DNS doesn't know the resolution of the domain name to the IP address, it will go and search higher level domain servers. And it also asks for no non-authenticated servers. And the query is, tell me what the IP address is of Intel. The reply that comes back is then has the flag of reply, of a standard query, defines whether it was a recursive lookup, and it will give the IP address that it's found and the server it found it from. So let's have a look at an example of this. So here we have our DNS lookup. So port 53 is the destination port which is used. So we can see here communication going back and forward between the DNS server and the client. Okay, so here is our first request, DNS. It uses UDP and the destination port is port 53. So here is the query. So you can see here that the flags that are set, that it's a response, and the message is a query, and the other fields that we have include the opcode and whether it's recursive. The reply that comes back looks something like this. So this is the response here, because the flag is set to a 1, and then we then see what the query was and then what the answers are, and eventually we can resolve the IP addresses. So in this case there are two possible addresses that we can use for our response when we connect. So try again. Oops, our connection isn't there just now, but the response that we will get relates to 92.122.126.176. One area that we might see malicious activity is with port scan. So there are tools which can be used to scan a network, and it is our task to be able to detect this type of malicious activity. So Nmap and hping are tools which can be used to assess any vulnerabilities in this respect. So you can see here there is a host at 75.1 and there is a destination of 75.132. So in this case this host is scanning this host initially on port 23 telnet, and then on the next port, which is 256, and so on. So this is the type of signature that we would see if someone was port scanning a host. The main types of scan that we get is a TCP scan. With TCP scan there is a full SYN, SYNAC, ACK, then a FINAC, so the connection is actually closed. So this is often the case where the application has been written at a high level and doesn't use a raw socket. We can have a SYN scan, and a SYN scan is where the the intruder sends a SYN, but the connection is never actually made. So this results in half-open connections, and often this is the case where the application has been written with raw sockets. Often the SYN flag is blocked by a firewall. So an intruder might use a fin scan because the fin is allowed to go through a firewall. And with this, closed ports often respond with a reset flag, but open ports ignore it. So we can see here an example of a port scan which is scanning on random looking ports 801433, which relates to SQL and so on. We can also have a port sweep, and with a port sweep a certain port is chosen. In this case it's the web port, port 80, and then a number of hosts on the network are then scanned for this open port. So this is often where the intruder is looking for a vulnerability in the infrastructure. So we can use Wireshark to be able to detect the presence of this type of activity. So we can see here that in this scan there is a great deal of traffic related to different types of protocols. We can see here there are only 4 packets related to each one, and that there is no traffic actually carried on each of these. Over here we can see a great deal of SYN activity and resets coming back, and again over here we can see the basic trace of SYN. So if we have a look at an example here, so we'll have a look at this one. You can see here there is the trace of a SYN on port 80. So let's see if we can find an Nmap one. It takes a little minute to load it. So with this, there's a great deal of SYN activity down here. So it's port all 8s, then 23, 256, 993, and so on. So we can have a look at that within Wireshark. You see there's a great deal of SYN activity. So this often shows malicious intent, and we possibly want to detect it. A SYN flood can be another sign of malicious activity, where multiple SYNs come in from an intruder's machine. So in this case we can see here that we have a HTTP connection, and we have the continual request for HTTP. So with this we can get a denial of service if an intruder continually tries to access on a certain port, or we can have a distributed denial of service where there are many hosts distributed across a network. An intruder will often try to cover their tracks, so we must be wary of spoofed MAC addresses and spoofed IP addresses. So in this case, an intruder sits at 192.168.75, but has spoofed his IP addresses to look as if they come from 10.0.0.1. So the IP protocol itself does not have any integrated authentication of the actual IP address of the machine. The same goes for a MAC address. It it is often fairly easy for an intruder to be able to spoof this address and send Ethernet frames from another node. Something else that we might need to investigate is the usage of application protocols. So application protocols are typically built around a request and a response. So in this case we have this is a sample of the HTTP request that a browser might send when it's accessing the default home page of a web server. So you can see there is a great deal of information inside this request, so such as the operating system that's used, the type of browser, even the host IP address, along with the supported content types. The reply that comes back is often a message, a response code, so in this case 200 says it's okay, and then we see other things that are sent to be able to define the date and where the content is. After this we see the actual content, the data being transmitted. So we can see here this header gets stripped off, and what we have left is this content, which in this case is the web page. So if we have a look at an example connection here, so we can see here's the SYNAC ACK. So the local source port is 2427 on port 80. So then the requester asks for the default home page. We see a response coming back, after which we then get multiple data packets with the actual content. So if we have a look at this in Wireshark. Okay, so we see our SYNAC ACK, and then this is the client asking the server for the home page, and then we then see the data being transmitted for this connection. So we can see there are multiple segments that are sent, so it is up to the client to be able to build these back into the original data. Sometimes we can get multiple TCP connections set up. HTTP itself was meant to be a fairly lightweight protocol where the connection was closed after the transmission was finished, but often there's a keep alive signal that keeps the connection open. An example of an auditing tool that can be used to detect when files have been changed is Tripwire. So with Tripwire we have an agent program which will watch certain folders or certain files as to when they change. These then get stored in some form of audit log, and we can set up events such as sending an email or an SMS message whenever something has actually changed. So let's have a look at a sample of this. Okay, so we can also have traces of activity on a machine that relates to network traffic. And if we have a Windows machine, there are certain folders that are set up that will monitor and keep a history of various activities. So in the recents folder we see any recent files that have been created. Within cookies we get a store of the cookies, so if a web page is accessed, if it has a cookie, then it will save it in the cookies folder. We can see Internet Explorer history inside this folder, and also this one, and there are various other ones such as the start menu and documents and so on. These are reserved as special folders. So we have a look at our toolkit. So we can actually look at the previous history of URLs. Again, this is stored inside the URL history folder. There are a number of special folders that we might look at in terms of an investigation. So we can have the recent folders. We can look at the cookies. So in this case, there's quite a few cookies in here. So it just takes a while to scan the folder. Then we can have application data, desktop, favorites, history, the internet cache, documents, pictures, and so on. There can also be hidden folders on a system. So you can see in this case there is a hidden file here. So when we do a normal listing, the file might not appear, but only when we do a search for hidden folders and files do we actually see them. And we can look at the file rights for each of our files and folders. Okay, so that concludes the presentation. So hopefully it's given you an understanding of some of the methodologies that we might use in investigating network traffic, a deeper understanding of some of the key protocols such as IP, TCP, Arp, Icmp, DNS, and a few application layer protocols. And we've also investigated some basic audit sources to determine network activity.